Hi, welcome to Mathematics with Tom. I am Tom, and today we're going to continue looking at our solutions to a second order linear differential equation with constant coefficients. So here's what we left with. Our solution, so a solution a solution to a s squared plus b times s plus c equals 0 is s equals negative p plus or minus the square root of p squared minus, we called it omega n. That was the natural frequency of the system, where p was b over 2a and omega natural squared is c over a. And also, just for clarity, let's do this. Let's write it this way. Let a, b, and c all be positive numbers. That'll help us as we describe our solutions in a bit. So what I want to do is I want to look at the different cases that arise from our solutions. So let's do that now. Our first case is this, number one. Our first case is when p squared minus omega natural squared is greater than 0. Okay. So when it's greater than 0, all of our solutions are going to be real numbers. And that's the key here. All solutions are real numbers. And you might see the notation that S, the solution, is an element of the real numbers. But that gives us this format. It gives us our null solution, yn, is equal to c1 e to the s1t plus c2 e to the s2 of t. Now, if you look at our problems, what we have is, since a, b, and c are all positive numbers, then p, this is going to just be a negative value. So all of our solutions now, are going to be, these are going to be decaying, or this would be e to some negative t, and e to another negative t. And so it's just it's just the sum of two exponentials that are both decaying. And if this term, this b, was a negative sign here, these terms would be exploding, but that's not the case that we're considering. So we have we're going to graph here in a moment. We're going to graph these solutions. So I'm going to be putting up number 2 right here. So I will give myself some space. Oh, and before we graph it, in this case, this system, we say that this system it's called overdamped. Okay, so I'm going to leave myself some space, and let's make a picture here. Okay, so here we have our graph. We're going to make we'll leave it. Now I'm going to make it a little lower here. I need my eraser, so let's bring that down. So if I make my graph, it looks like about like this. Here's my t-axis, and I have a y of t axis. And so when my system is overdamped, it has some initial starting value. We'll call this our initial starting value, y of 0. And overdamped systems are historically drawn in green. Just kidding, they're not. But all it is just a system that just has decaying exponential growth. And so this is our overdamped solution, or overdamped system, overdamped. Okay, next, let's look at our second case. So I'm going to come over here. My second case is this. It's when p squared minus omega natural squared is equal to 0. And what happens here is I have a repeated solution. My solution is just minus p, but I have 2 of them. And it comes from, so let's do this. This is repeated roots. Repeated roots. For example, so let's do an EG. For example, a system that might have that would be a very simple example would be s squared plus 2s plus 1 equals 0, because it factors into, s plus 1, it's kind of a funny s plus 1 squared equals 0. So s, or we'll write it that way. So our solution is just s is minus 1 and minus 1. But when you write the solution, this is what's interesting. Our null solution now is, it starts out as we would expect, c1 e to the st plus, but now we pick up a c2, and they can't be the same. They become different by a factor of t e to the st. Now, let's take a look and think about how that solution might look. Because what happens is this. When t equals 0, so at time is 0, then what happens is c2 t e to the st, this whole term is 0. Well, but also when time is 0, e to the 0, that's just 1. And so there you have it. You have that your initial condition, y of 0, is c1. So let's put that up. We'll put that in yellow. Let's put that in yellow. So my initial condition, where my graph is going to pass through at time 0, that's the value c1. Next. The next thing is, we don't normally think about negative time, but in this case it's interesting in that these two terms are exactly the same except for the t. When t is negative, this term becomes negative. And if you graph it, what happens is your negative solution would be negative. It rises up to your initial condition, and just for a moment t seems to it tries to overpower a decaying e, but we know that from calculus that nothing can grow like e, an exponential, and so also it approaches 0. This system, this is, we say, this is critically damped. This is a critically damped system. Damped system. And let's write that up here, our yellow. This is critically damped. Critically damped. Now, case 3. All right. Our last case is case 3. And this is when p squared minus omega natural squared is less than 0. It's a negative number. And so what we do is we let omega d squared equal p squared minus omega n squared. This d, this stands for damped. So our damped frequency. And what happens then is we have that our solution S is equal to minus p plus or minus I times, because this is a negative value, we're going to have I times the square root of omega d squared, or more simply we write this as minus p plus or minus I times omega d. So notice this. You can say this is in the complex numbers. Because this is a complex number, there's going to be a sine and a cosine factor here. So our system is going to oscillate. It'll oscillate based on I omega d, or omega d, and at the same time it's going to be approaching 0 because you're going to have an e to this. So our solution is going to look like like this. Y null is C1 e to the minus p plus I omega damped plus C2 e to the minus p minus I omega d. So let's expand this just one. We'll expand just this one term. If I expand it, it's C1 e to the minus, oops, I'm sorry, there should be a t. Oh goodness, let's put a t on there. There we go. So e to the minus pt. So this is decaying. This is decayed. Times e I omega d t. This term, this oscillates. This oscillates by sines and cosines, and we could do that with our x. Our next one is going to be a C2 e minus p times t times e to the minus I omega d t. And again, here's our oscillating term, and here's our decaying term. So let's graph that. Oh, and by the way, this kind of a system, we call this system is called underdamped. And we'll come over here, we'll graph that, and I have, when we graph this, let's graph it with our pink. Definitely a pink one. And what's going to happen is the system will have some initial condition. Maybe it starts the same as our green one. And what's going to happen is it wants to come down. It wants to oscillate, but at the same time, we have this decaying or this stopping of it. And so each time it oscillates, the oscillation becomes smaller and smaller until it begins to zero out at the end. Okay? And those are our 3 cases. Thanks for watching.